Today we're going to take a look at the vector cross product. So remember, previously we defined what we called the vector dot product. So the dot product, if we took A dot B, the result was a scalar. So that was a type of vector multiplication that resulted in a scalar number. Here, we are taking two vectors, A and B, and we are multiplying them in a way that results in another vector. So with vector multiplication, we have to notice that we have different multiplications. The dot product, or scalar product, gives us a scalar, and the cross product, or vector product, results in a vector. This is the definition of the cross product. However, this is not the way that we are going to think of the cross product or calculate it. And we're going to use something called a determinant. So an order 2 determinant looks like this. So we'll have, it's like a matrix, but we have these vertical lines. If it was a matrix notation, we would have these as large square brackets. So instead, suppose we have, say, X, Y, Z, W. The way that you compute a 2 by 2 determinant is you go top left times bottom right. So in this case, XW minus top right times bottom left. So minus YZ. So there's our determinant of order 2. And the way we deal with this for a cross product is as follows. We use an order 3 determinant. And we do it in the following way. And it turns out that that cross product formula is exactly equal to this determinant. And so the way you do it is in the top row, we're going to put vectors I, J, K. And remember what those vectors are. I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. So these are our three standard unit vectors in three-dimensional space. Once we have this, we then first put the entries of A, so A1, A2, A3, and then after that we put the entries of B, B1, B2, B3. And the way that we calculate a 3 by 3 determinant, and by the way, those of you who take a course in linear algebra will see more of this. This is just a use of how we do determinants in linear algebra. But the way that we do this is as follows. This is going to be equal to the sum of 3 of these 2 by 2 determinants. And the way you set that up is for the first determinant, we're going to use the top row. So we're going to have an I. And that's multiplied by a 2 by 2. Then we're going to have minus J multiplied by a 2 by 2. And then plus K multiplied by a 2 by 2. So what's happening is the entries in the top row are each getting their own 2 by 2 over here. And the signs have to go plus, minus, plus. And the way you get these 2 by 2s is as follows. So take, for this first one with I, take the row and the column that include I, erase those, and what remains, give us our 2 by 2. So in this case, 2 by 2 for the I term, we just write that right over here. So we have A2, A3, B2, B3. Then we do the same thing for J. Erase the row containing J and the column containing J, and what remains is the 2 by 2 for J. So what remains when we get rid of the row and the column including J is A1, A3, B1, B3. And finally, we do the same for K. So erase the row containing K and the column containing K, and what remains is this 2 by 2, which is A1, A2, B1, B2. And then each of these 2 by 2s is calculated using this idea over here. So these are usually best learned by practice. So let's see an example of how we might do one of these. So first example here, we're given 2 vectors and we're asked to compute the product A cross B. So let's set that up. And we set up our 3 by 3 with I, J, K as the top row, then the entries of A, 1, minus 1, 2, and the entries of B, 2, 1, 3. And again, break it down. We're using the top row, so we'll have 3 2 by 2s, 1 for I, minus 1 for J, plus 1 for K. Now to put in the entries of these 2 by 2s, for the 2 by 2 that goes with I, erase the row containing I and the column containing I, and this 2 by 2 down here in the bottom right is what we want. Minus 1, 2, 1, 3. For the 2 by 2 that goes with J, erase the row with J and the column with J, so we get 1, 2, 2, 3. And for K, erase the column and the row with K, and we get this 1, minus 1, 2, 1. And what we do now is just go through one at a time and evaluate these 2 by 2s. And you want to be very careful when you do these. It's easy to make algebraic mistakes. So the first, remember, top left times bottom right, so minus 1 times 3, minus top right times bottom left, so 2 times 1. Then we have minus J, top right times bottom left, 1 times 3, minus, top left times bottom right, 1 times 3, minus top right times bottom left. So 1 times 3 minus 2 times 2, plus K, top left times bottom right, 1 times 1, minus top right times bottom left, which is minus 1 times 2. Simplifying, we have I times, we have minus 3 minus 2, so we have a negative 5. Minus J, we have 3 minus 4, so that's a negative 1. Plus K, 1 minus minus 2, so 3. So this is minus 5I plus j plus 3k, which we can also write in this vector notation, minus 5, 1, 3. So this is our cross product. This, note again, we took two vectors. This type of multiplication yielded another vector. So the next thing we want to think about is what is this vector? How does it relate to A and B? Well, one thing we can note is what happens if we take A, so one of the vectors we started with here, and we do the dot product with this new cross product, A cross B. So A is the vector 1, minus 1, 2, and A cross B we just computed as minus 5, 1, 3. And remember, when we do a dot product, we multiply the individual components and then add those products. So first component, 1 times the first component, minus 5. Plus second component, minus 1 times second component, 1. Plus third component, 2 times third component, 3. So this is 1 times negative 5, minus 1 times 1, plus 2 times 3, or minus 5 minus 1 plus 6, which is 0. And if we remember, when we studied the dot product, what does that mean? If two vectors have a dot product of 0, it means they are perpendicular. So this tells us that the vector A is perpendicular to the vector A cross B. It's also going to be true that if we chose B, the vector 2, 1, 3, and we took the dot product with our new cross product, we would also get 0. And that is one of the key properties. Orthogonality, by the way, orthogonal is a synonym for perpendicular. So, for any two non-zero vectors, A and B, the cross product of A and B is perpendicular to both A and B. And this is probably the key property of cross products that we tend to use in calculus. Okay, if they're perpendicular, and by the way you can picture it would be, let's imagine our two vectors in 3D. So if this is A and this is B, A cross B is, again, perpendicular to both A and B. And this is a good time to mention it, but this is actually also an operation that is not commutative. So what I mean by that is A cross B is different than B cross A. What happens is B cross A points in this other direction. It's in the opposite direction of A cross B. We'll mention that in a set of properties in just a minute. But here we're talking about an angle between vectors. So this angle, in the case where you have perpendicular vectors, the angle is a right angle. And this should come as no surprise, because now we have a result for the angle between vectors in general that involves the cross product. And if you remember to last lecture, we had a similar result for the dot product where you had a cosine instead of an angle theta. So what this result is telling us, we can take a look at the geometry. So now in this more general setting, if this is B and this is A, then this right-hand side is nothing more than the area of the parallelogram formed by A and B. So let's actually extend this B and A to make this parallelogram. And what we have here is a height. If this theta, this is our angle between the two vectors A and B, the height of this parallelogram is, it's coming over and using this leg of this triangle. And so you want to think of your SOHCAHTOA rule. So sine is opposite over hypotenuse. So the length of this B, well, the length of this vector here is the length of B. So this opposite is going to be the length of B times sine of theta. So the area of this parallelogram is the length of this base, which is A, times the height, which is B, length of B times sine of theta. And it turns out that, again, this right-hand side is equal to the length of the cross product. You have to recognize that this is saying take the magnitude of the vector A cross B. So this often comes up in area computations. Typically, if you want the angle between vectors, you actually use the analogous result that we had for the dot product. Remember, for the dot product, it was A dot B is the length of A times the length of B times cosine of theta. Now, you could use either of these formulas to recover the angle in between the vectors A and B, but it's just generally easier to use the one for the dot product because the dot product is quicker to calculate than the cross product. That being said, if we want to start talking about areas of parallelograms, that's really when we start to use this result. And again, we can use the right-hand side or compute A cross B and take its magnitude, and that will give you the area of this parallelogram. So let's use this in an example and see how we would do it. Find the area of a triangle with these vertices. Well, one thing that we notice is when you're given 3 points, say 3 points can make a triangle and also a parallelogram. And a triangle's area will be half that of the parallelogram formed by those 3 vertices. So if we want to picture what we're doing here, which is always helpful when you're doing calculus in higher dimensions. And when we're working in 3D, we usually have the x-axis coming out of the board. And so our points A, we have 1 along the x-axis, 6 along the y-axis, 8 along the z-axis, so this is our point A. For B, 2, 4, 0, so B is actually in the xy plane. And then C, 1, minus 4, 5. So the triangle we're after is this one. And we want its area. And again, what we want to do is to create a couple vectors. And then with those vectors, we'll have a parallelogram. So, and you can pick any two vectors here, as long as they're not parallel. So we could do, say, the vector from A to C. And then we could do the vector, say, A to B. If we take the cross product of those two vectors and take its magnitude, we will get the area of the parallelogram formed by them. And then we know that the area of the triangle is exactly half the area of that parallelogram. So let's form our vectors first. So remember, the way we do this, the vector from A to B, we take the coordinates of B and then subtract the respective coordinates from A. So we'll go 2 minus 1, 4 minus 6, and 0 minus 8. So again, take the second coordinate from B, 4, subtract the second coordinate from A, 6. Take the third coordinate from B, 0, subtract the third coordinate from A, 8. And this gives us the vector 1 minus 2 minus 8. We then do the same procedure for AC. So we do 1 minus 1, negative 4 minus 6, negative 8, negative 5 minus 8. So we have 0 minus 10 minus 13. No. Minus 3. Okay, now we know, again, the magnitude of the cross product will give us the area of the parallelogram formed by these two vectors. And we know that our triangle's area is exactly half of that. So the area that we seek will be 1/2 times the magnitude of the cross product AB cross AC. So to use this now, we need to do our cross product. So let's get that set up. AB cross AC. And by the way, again, any two non-parallel vectors would get you to the same answer. So we set up our determinant, I, J, K. We put in AB first, so 1 minus 2 minus 8. And then we put in AC, 0, minus 10, minus 3. And we work through our cross product. So this will equal, remember, I times its 2 by 2 minus J times its 2 by 2 plus K times its 2 by 2. To get the 2 by 2 for I, erase the row and the column containing I. What remains? Minus 2 minus 8 minus 10 minus 3. For the 2 by 2 that goes with negative J, erase the row and the column with J. We get 1 minus 8, 0 minus 3. And then for the 2 by 2 that goes with k, we erase the column and row containing k. 1, minus 2, 0, minus 10. Okay. Remember, now to do the 2 by 2s, top left times bottom right, minus top right times bottom left. You want to be careful because you have a lot of minus signs floating around. So minus 2 times minus 3 minus minus 8 times minus 10. Okay, minus j. So for j, we have 1 times minus 3 minus negative 8 times 0. For k, we have 1 times negative 10 minus negative 2 times 0. Which simplifies, let's see, here we have positive 6. 10 times 8 is 80. So we have 6 minus minus minus. So 6 minus 80 or minus 74i here we have 1 times negative 3 plus 0. So this is a minus 3, but there's a minus sign out front, so that's plus 3j and here we have a 1 times negative 10 plus 0, so plus 10k. Or the vector minus 74, 3, 10. What we now need is the magnitude. So remember, by the way, you could have done AC times AB if you wanted. Though the vectors would point in opposite directions, they would have the same magnitude. But let's now take the magnitude of this and plug it into our formula. So we have that the area of the triangle, again, remember it was 1/2 times the magnitude of the cross product of these two vectors, or 1/2 times the magnitude of the vector minus 74, 3, minus 10. And our formula for the magnitude, we know we take the square root of the sum of the squared entries. And so this gives us the area of the triangle. So again, with area computations, the cross product often comes up as a tool. And in fact, going forward, the cross product will be very, very common as a tool. It's kind of unusual to be asked on a calculus test, here are two vectors, compute the cross product. We are typically actually using the vectors, or constructing vectors, and then getting a vector perpendicular to those two vectors. So that this key property, the fact that if you take any two non-zero vectors and you cross them, the cross product is perpendicular to both, is extremely useful going forward in multivariable calculus. Okay, that being said, let's talk about some algebraic properties of the cross product. The first is what we mentioned earlier. This again is what we call non-commutativity, which is a fancy way of saying that if you switch the order, you change the math. So if A cross B is not B cross A, it's negative of B cross A. So this just means, again, that they point in opposite directions. If K is a constant, you can do KA cross B. You can move that K over to B. Or you can do A cross B and then multiply by K outside. All results in the same thing. And then we have these different laws. So we see this distributive law where the cross product distributes over addition. And then we see this product here where you involve both a dot and a cross product. This is essentially saying you can actually switch. You can change this to a cross and this to a dot, and you get the same result. And then here is another way of calculating this double cross product. These are not properties that we will use very much in this course, but they are helpful for understanding how to use cross products. The last topic comes about with this idea of a parallelopipet. So a parallelopipet is the analogous three-dimensional object from a parallelogram. So take vectors in 3D and then with them now form all the parallelograms you would need to form this box. And so just think of it as a box that has angles that are not necessarily right angles. And if we want to find the volume of this, we use what's called the scalar triple product, which is this A dot B cross C, which is one of the terms that showed up in our previous theorem. So note over here, this was our scalar triple product, the fourth line. So this is a way of getting the volume. And remember, B cross C, this is a vector, but then once you take this vector and take its dot product with A, then you get a scalar. So again, this gives you the volume. And this is often a handy tool to check. So it's useful to check if A, B, and C are what we call coplanar, which just means that they lie in the same plane. So if A, B, and C all lie in the same plane, then think about this parallelepiped. It's a box with a height of 0, which means it would have 0 volume. So if, this is how we use this, if A dot product B cross C equals 0, that means that this parallelepiped volume is 0, which then means A, B, and C lie in the same plane. So this is a handy use of the scalar triple product and the fact that it gives you the volume of the parallelepiped formed by your three vectors. And again, if that volume is 0, then you know the three vectors lie in the same plane. So this is the basics of the cross product. This is something that in calculus, in multivariable calculus, it is critical to be comfortable with the cross product and be able to calculate them quickly, efficiently, without error, because it comes up as a tool in many different contexts going forward in multivariable calculus.